And the next speaker is Miroslav Stepanek from, I think, Charles University, Prague, Czech Republic. So, please.
Okay, firstly, let me thank the organizers for giving me the opportunity to have a presentation on this wonderful workshop. Actually, what I'm going to talk today was motivated by my colleagues who do computer simulations of polyelectrolytes, and they were curious how good are their models of polyelectrolytes with explicit counterions in catching reality. So we thought what could be done in comparing their models with experiment, and since in our laboratory we use fluorescence spectroscopy quite often, and fluorescence spectroscopy is very good in assessing local properties on a nanometer scale, we came to the idea that we would perform this study, that we would try something very simple and very fundamental. Basically, there are two ways to measure counterion concentration, local counterion concentration around the polyelectrolyte chains by fluorescence spectroscopy. First possibility is to use collisional quenching of fluorescence by heavy ions. So if we use heavy counterions such as iodide or cesium or thallium, we can measure quenching, and then if we plot the ratio between the either fluorescence intensity or fluorescence lifetime in the absence of the quencher to the same quantity in the presence of the quencher as a function of the quencher concentration, you will end with this linear dependence if everything goes regularly, and we can assess the quenching constant. And the second possibility is to use fluorescent pH indicators for measuring H plus concentration. And here again, we from the fluorescence measurement, we obtain the fluorescence titration curve, and from this titration curve, we obtain the pK, which is generally shifted from the pK of the probe, which is just in the bulk solution. So what we measure in this measurement is either local pH, that we measure the local concentration of H plus ions in the vicinity of the chain, or effective pK, so that this effective pK can be interpreted as a dissociation constant, which is influenced by the fact that there is a local electrostatic potential that affects the proton and changes the dissociation properties of the fluorophore. So as an example that we actually used in this study is this dissociation of umbelliferone, which is the weak acid, with the dissociation constant of 7.85, and the neutral form of the probe is non-fluorescent, and if it undergoes dissociation, the anionic form emits nice blue fluorescence. So in this study, what we have taken for this study was polyelectrolyte acid, which was synthesized by using fluorescent ATRP initiators. So instead of labeling the fluorescent chain, we'll build the chain from the fluorophore itself. And we use two ways to prepare it. If we use the monofunctional initiator, we ended with the fluorophore at the end of the chain. If we use the bifunctional initiator, we ended with fluorophore in the middle of the chain. For the monofunctional initiator, we have taken either 2-bromo-methylnaphthalene for the quenching studies, or 4-chloromethyl umbelliferone for the local pK measurement. And the bifunctional was the 2,6-bromomethylnaphthalene for the quenching measurement. This is a little bit more about the chemistry. So this is how the labeled PMA was synthesized in the case of bifunctional initiator. So here we have the bromomethylnaphthalene, which reacts with terbutyl methacrylate. We prepare the precursor, and then is later being hydrolyzed by trifluoroacetic acid to labeled polymethylic acid. In case of umbelliferone labeled polymethylic acid, we firstly need to prepare the fluorophore, which is not commercially available. So by this reaction, we prepare the chlormethyl umbelliferone, and in the same way, we prepare the test-butyl acrylate, and it's in the final step hydrolyzed to having this umbelliferone labeled polymethylic acid. Now, little bit about the simulation. I'm an experimentalist, so I will not go to details because I would walk on a thin ice in my case. But what's important to keep in mind that really the methodics of the simulation is the same in the case that we study the quenching and we study the local pH, because for the simulation only the electrostatic interaction of the ion with the chain plays a role. So H plus is the same for the simulation as the cesium. So for the simulation we use this chain with composed of 61 beads. There are 3 chains in the box which emulates the concentration of 1 milligram per milliliter, which is used for the experiment, and these beads are interacted by the generic sphere energy potential. And what we actually follow in case of local pH measurement, only the concentration of the counterion is important. In the case of the quenching study, what the simulation does is that measures the collision frequency of the ions with the fluorophore. So the collision is encountered if the certain cutoff distance between the fluorophore and the counterion is achieved. And from the collision frequency, we can calculate the shortened emission lifetime and compare it with the experiment. So these are the experimental results for quenching. So this is the naphthalene labeled polymethylic acid, and if we add various amounts of cesium chloride, it leads to quenching, which is manifested by the decrease of the fluorescence lifetime. And if we plot this fluorescence lifetime in this dynamic Sternformer plot, we can see that for the free probe, the quenching is much less efficient than for the labeled polymer, because of course the cesium ions are attracted to the polymer chain, and this attraction is much higher for the chain in which the naphthyl group is in the middle than for the chain in which it is in the end of the chain. So now, when you compare it with the simulation at various concentration of indifferent salt, of course, the adding salt, indifferent salt, causes screening the electrostatic interaction between the chain and the quencher ions, and it decreases the efficiency of quenching. But what is important to see here that these points are the experimental data, and these lines are the data from simulations. The simulation, it's not a perfect match, but at least semi-quantitatively, it provides a good agreement with the experimental data. As regards the local pH measurement, so firstly, we little bit characterized our umbelliferone labeled polymethylic acid by various techniques. So this is the small angle X-ray scattering curve. It can be nicely fitted with the long cylinder form factor, which provides these parameters, length and radius, which are in good accordance with the hydrodynamic radius from dynamic light scattering. And if we measure the dependence of the zeta potential and the hydrodynamic radius of the polyelectrolytic acid on pH, we see that the transition occurs somewhere about the pH 6, which is very important in our case because if you remember, as I show you the second slide with the umbelliferon dissociation, that the pK of the probe is about 7.8. So all the processes that we are interested in occurs in this case in this region. So we can consider for our purposes that the polyelectrolytic acid is fully ionized in the region where the fluorescent label undergoes dissociation. Here again, you can see that from the fluorescence anisotropy measurement that the probe, the label at the end of the chain rotates quite freely in the range of the pH, which is relevant for the measurement. This is just to remind you about the correspondence between the local concentration of the ion and the electrostatic potential around the polyelectrolyte chain, and that if we take this equation together with the definition for the dissociation degree and the dissociation constant, we end with this equation which puts into correspondence the effective pK that we measure and the local electrostatic potential. And now if we measure the spectra of the labeled polyelectrolytic acid as a function of pH, we can see that this is the excitation spectra, the form that corresponds to the anion goes down with decreasing pH, the protonated form goes up, and of course the emission of the fluorophores goes down with decreasing pH, and this is how it can be seen by measuring fluorescence titration curves. And again, there is a shift of the pK for the labeled polymer as compared to the free umbelliferon. And again, there is a screening. So if we take various concentration of sodium tetraborate at the beginning, the higher is the concentration, the smaller is the shift of the pK because of the screening of the interaction of H+ with the polyelectrolyte chain. What is interesting is that if we measure zeta potential by means of electrophoretic light scattering, and we calculate the zeta potential by using the Smoluchowski approximation, and we put it to this equation, we achieve the results which are in very good correspondence with the results which are from the fluorescence measurement, which is interesting because there is no particular reason, or at least we don't have explanation why the match is so good for the zeta potential, which is taken from electrophoretic light scattering measurement. Before I go to the comparison between the fluorescence data and the simulation, there are just a few parametric studies on how various properties of the chain are influencing the results in simulation. So these are the various polymer concentration. You can see that the influence on the pK shift is not big. The same is the case of the degree of the charge density, and what only has the influence from the parameters that we tested is the distance of course the distance of the ionized group from the polyelectrolyte chain. The far is the distance, the less is the influence of the electrostatic potential of the chain on the data, and of course there is smaller shift. So it can be, for comparing the experimental data with the simulation, this spacer length must be set properly in accordance with the actual distance of the length of this fluorophore. And if we do so, we can obtain the titration curves from the simulation, and we can compare them with the pK shifts from the experiment. Again, the match is not perfect, but in both cases, we are able to see the shift of the pK affected by the electrostatic screening of the added salt. So to conclude, I have shown you that fluorescence measurement probes the local ion concentration by both measuring the quenching and pK shift of fluorescence pH indicators. And I also show you that fluorescence measurements are in semi-quantitative agreement with simulations. What was interesting finding that the fluorescence measurements are in good agreement with pK shift, which are obtained from zeta potential measurements. And the last, what was found by simulation, that neither chain length nor the polymer concentration affect the pK values which are obtained from simulations. So I have to acknowledge my funding, and of course I will thank you for your kind attention.
Thank you very much for your presentation, and we have perhaps some time for a few questions. Yes, please.
It's more of a comment. First, I think you're a bit modest. It's better than almost quantitative correspondence. But the reason, I think it's rather well known, I mean, through my comment, that there are cancellation of errors in the approximation of Poisson-Boltzmann equation, which works to its favor in the final results. And I think we've seen this when we are dealing with the systems with monovalent salt. That's my view of it from a lot of work in the literature, where you often get very good correspondence.
Well, at least
for salt effects using the Poisson-Boltzmann approach.
At least as regards the pK shifts, it was used many decades ago for interfaces, but as regards the polyelectrolyte chains, not very often. So.
Any more questions? Okay, I have one question, because I was a little bit concerned. You mentioned that you had a long cylinder, and it was 46 nanometers. And then I was wondering, then you said that the hydrodynamic radius of that was 40 nanometers. And how did you measure that? Because that means that you didn't have, you could not use the Stokes-Einstein relation.
Yes, well, if you take the equation for the diffusion coefficient of the translation diffusion coefficient of the cylinder of that parameters, you end exactly with what we find.
But then you use the polarized light scattering. Because otherwise you cannot separate what's coming from the translational diffusion and the rotational diffusion. Okay, yes, well you are right, we didn't use that, but the discrepancy was really small. So what the theoretical formula for the diffusion or for the hydrodynamic radius of the cylinder of that size tells us that it should be something like 12 nanometers, and we measured something like 14 nanometers. Okay, because I was wondering the same with the zeta potential, because if you not have the electrophoretic mobility, but you have the zeta potential, it means that you probably use the Henry's law for calculating the zeta potential.
Yes, that's a Smolkovsky.
Yeah, because
Smolkovsky
that is also
approximation.
based on spherical symmetry. So that was my. But thank you very much for